Welcome back, IB kids. Mr. Tima here for part two of our gravity and free fall notes. Okay, so you just talked about free fall. Remember, we watched the astronauts drop the hammer and feather in outer space, and they hit exactly the same time, like the vacuum of outer space, without any resistance. The problem is on Earth, we got a big deal. We got this thing called air resistance. Okay, if you notice, our elephant and our feather aren't falling at the same rate on the left. The elephant comes crashing down much quicker, and approximately 3 minutes later, it says the feather finally reaches the ground, which is what is expected on Earth. Air resistance, by definition, is the force that opposes the force of gravity. Okay? It is the amount of air resistance depends on the object's shape, size, and speed. Now, shape and size are pretty easy, right? Like the elephant's bigger. Okay, you know that if you have a parachute that's really small versus a parachute that's very large, that's going to do things. All right, but speed's something we don't think about, but you should, like your car or people that are downhill skiers and stuff. How many of you have ever stuck your hand out the window of a car when it's going pretty slow? You feel a little breeze. It goes up a little faster. It might be kind of fun to keep it out of there, pretend like you're going to lift the car off into flight. But if you stick your hand out the window when you're going down 270 at 80 miles per hour, it's going to like rip your arm back. Okay. And it has nothing to do with anything but your speed hitting the particles of air. We don't think about that. We think about the air blowing onto us. But in essence, you kind of make your own wind per se because you're running into the particles of air. The same thing, it can be super hot outside and you go for a bike ride. Well, it feels cooler while you're riding your bike and pedaling because you are forcing yourself through the particles of air. Kind of goes back to that relative motion thing we talked about earlier in class. So take a leap of faith, okay? Free fall in motion. The whole point is you aren't losing any weight when you open the parachute. You have exactly the same weight. All that parachute, all those cords, everything were attached to you. It's when you open it, all you've done is increase your size and shape, which increases your air resistance, which means it basically slows you down. Your air resistance vector has gotten bigger. Love this demo. I love this demo. If you actually look at the force diagrams of this demo, it makes a ton of sense. So let it run a couple times and let's look here. Watch our little dude. Gravity's the only thing acting on him. And then all of a sudden, the air resistance on the body becomes equal. And then all of a sudden, he opens it. Now our air resistance gets bigger, but then it starts to catch up to gravity. And we get to that. That's called something. It starts with a T. It's called terminal velocity. The forces on a falling object are balanced, and the object falls with a constant speed. When you first jump out of the plane, gravity's pulling on you. You're accelerating, but your body will only accelerate to a certain speed. Like right now, our guy's falling. Boom. Right now, we've hit terminal velocity. When he opens the parachute, we hit a new terminal velocity. Okay? Both are constant velocities. The problem is your body falling hits a terminal velocity, like right here, that's probably at about 150 miles per hour. But when you open your parachute, you're down to 30 miles per hour when you hit the ground. Okay, a lot of people still get injured when they come to the ground on a parachute. The difference is you can survive a 30-mile-an-hour car crash. You can't survive a 150-mile-an-hour car crash. All right. So, have you ever heard the myth about someone dropping a penny off a super tall building and it go and kill somebody because it just keeps going faster and faster and faster and kills somebody? Well, let's see if it's right.
Writing's not that easy, but Grammarly can help. This sentence is grammatically correct.
This myth originated in the Big Apple, atop an architectural icon, the Empire State Building.
The myth is that if you throw a penny off of a building this height, that it'll either get going so fast that it'll embed itself in the concrete at the base of the building, or it'll hit somebody in the head and kill them.
Adam and Jamie need to find out what is a penny's maximum speed when falling. In other words, its terminal velocity. Once they've done that, they'll shoot the coin at concrete, asphalt, and a head made from ballistics gel. It's time to see if Jamie's penny can achieve terminal velocity. The modified staple gun blasts the coin from 3 feet at the concrete block.
Look, you can see the penny imprint.
The penny traveled the 3 feet in 16/500ths of a second.
The rig has shown that we can fire this penny at about 65 miles an hour, which is at the upper level of what studies have shown that the terminal velocity of a penny would be.
So the test shows that a coin traveling at terminal velocity cannot penetrate concrete or asphalt. But what about flesh and bone? Remember, the penny myth talks about a penny shattering someone's skull. Enter Norma, Adam's ballistics dummy. Norma's cranium will take the full brunt of a penny traveling at terminal velocity.
Lights. Perfect hit. Lights off.
The penny broke through the thin layer of ballistics gel, but the skull is intact.
So, you ready to put that to the ultimate test? We've tried it on all the other stuff we've got. Want to try and catch it in your hand?
The penny is leaving an imprint in the concrete when it hits. So, I'm a little hesitant about catching it, actually.
The Mythbusters are about to find out what happens when a penny traveling at 64 miles per hour hits skin.
I'll do it.
Okay.
But you got to do it too. Otherwise, you're like a wuss.
Okay, you first.
Okay. Still a wuss.
I'll kick your
Penny for your thoughts right about now, Adam.
I'm scared.
Okay. 3, 2, 1.
Ow! That didn't actually hurt that much.
Well, Jamie, take cover because Adam's taking aim.
All right. Firing. And 3, 2, 1. Well, that seemed to work like a charm.
Look at that imprint. You can clearly see where it hit.
The penny is shot from the slot at almost 3 times the speed of sound.
The high-speed camera result apparently is 3,000 feet per second.
Well, that's like a bullet. That's the speed of a bullet.
The coin still did not end up embedded in the block.
64 miles an hour just wasn't enough to cause any kind of damage to a person. And then when we made it go almost 3 times the speed of sound, it still wasn't enough to break the bones.
Yeah, I mean, the worst thing I can come up with is if you were looking straight up in the sky and you got hit in the eye, it probably wouldn't be very good for you. But even then, I don't know whether it'd take your eye out.
I think we busted the heck out of this one.
Myth busted.
Yeah.
Myth busted. Okay, perfect. Excellent. So remember, terminal velocity. It's all about the vectors, okay? So for example, a balloon reaches terminal velocity as the forces become balanced. Notice the buoyant force is also present. Okay, there is this thing called the buoyant force, which is just kind of the upward pull of the particles that are in it. Okay, but for example, we're not at terminal velocity here. Our velocity down is greater than our buoyance force. Right? We're still not at terminal velocity here because these forces are not balanced yet. But when we add them all together and we start traveling, once we put that buoyant force in there, now if you notice the vectors all together equals 0. So we'd say that that balloon, even if it was falling, but if our vectors are equal, they become terminal velocity. I took this out of the Columbus Dispatch or USA Today a long time ago, but it kind of makes sense. And in Ohio, we think about that. Snowflake. A snowflake takes 75 minutes at terminal velocity to come out of the sky. They fall very slow. Okay, snowflakes do. That's why sometimes when you look at the radar and you're hoping for that snow day, you'll see like the blue and you think, oh, it's snowing. And you look outside and there's no snow. Because as soon as that hits, it's snowing way above us. But it takes to fall about 2 miles, it takes about 75 minutes, about an hour and a half, an hour and 15 minutes for that snowflake to reach the ground. Now, raindrops fall a lot faster. They have a higher terminal velocity. About 8 minutes. Okay. And they come, and if you've ever been outside in a big rainstorm, it kind of hurts. Those big raindrops hitting you will hurt. The thing is with rain, though, rain kind of makes this like bevel shape because it kind of forms to that shape that it kind of slows it down. Now, if this is hail, piece of ice, it's going to come really fast. It'll only take a couple minutes. And if you've ever been out when it's hailing, it kind of hurts. Obviously, a skydiver, they get into like that flying squirrel position to kind of slow themselves down and enjoy for a little bit. But somebody that's falling in an average mass human, they say an average mass human here is roughly about 150 pounds. Okay. He's going to fall at 120 miles per hour. Okay. Take less than a minute to travel 2 miles. Okay. So you basically, when you go skydiving, you go up about 3 miles. You only get to fall for about a minute and a half before you have to pull your parachute. And then at Cedar Point, they have this thing. They have this thing called the power tower, and they drop you, and it's kind of intense. And you actually can do it. You used to be able to hold a penny out in your hand, and the penny would actually come off your hand and float for a little bit because you're both falling at the same rate. And then they have this thing called the Vomit Comet. Okay, have you ever heard of the Vomit Comet? Well, we're going to talk about it right here.
I'm about to experience weightlessness. For the first time.
Injection. Now you're freezing.
Oh my god. Oh my god. That is so strange.
Oh my god. Oh my god.
This is totally freaky. This is way better than I expected. I'm just going to say this right now. I'm going up to the ceiling, and here we are. I am ridiculously excited because behind me is a zero-G plane. I'm in France. I was invited here by the YouTuber Bruce. This is Bruce. Diana, physics girl. We are going flying some parabolas. We're going into zero-G. It's going to be awesome. Come on. The principle behind weightlessness is pretty simple. The plane and everything inside it just need to accelerate towards the Earth at the same rate as a freely falling object in a vacuum. That is 9.8 meters per second squared. So you can think of your body as this pen and the plane as this bottle. And when it's freely falling, there's no contact force between the pen and the bottle, and so the pen feels weightless. So you might think the way to do this is just to put the plane into a dive, but that's not actually how it works. Instead, the plane starts climbing at a steadily increasing angle. With no windows inside, it's impossible to tell that this is happening, and all you feel is pressed into the floor with a force 1.8 times your body weight. This is because the plane's acceleration is directed upwards and perpendicular to the floor, and it makes standing very difficult. Not only are you nearly twice as heavy, all the blood drains from your head and into your feet, which made me pretty dizzy. So weak! Lying on your back is much more comfortable, and we're advised not to move our heads around and look straight ahead, because in hyper-G, our vestibular system is hypersensitive to movement, which can lead to motion sickness. And that's why this is sometimes called the Vomit Comet.
I kind of like this.
It is fun. Feels like someone lying on you.
Yeah.
And I like that.
Yeah.
Once the plane is climbing at about 50 degrees, the engines are ramped down and the plane is put into a parabolic trajectory. It's at this point that you start experiencing weightlessness. I can feel myself getting lighter. Whoa, that is such a strange feeling. That is so weird. The plane and you are still moving upward, but you are accelerating downward. There's Diana. She's the physics girl. Then the plane peaks and starts speeding up again towards the Earth. This is totally strange. The whole time, the plane is accelerating toward Earth with the same acceleration as a free-falling object in vacuum. The pilots have to very skillfully adjust the thrust to perfectly balance air resistance and maintain exactly this acceleration.
Okay.
Oh my goodness. How do you feel?
It's incredible.
So it's like throwing this bottle into the air. The pen inside experiences weightlessness from the time it leaves my hand until it comes into contact again. After 22 seconds of weightlessness, the pilots pull out of the dive, again subjecting us to hyper-G as the plane accelerates upwards. In total, we performed 13 of these zero-G parabolas, plus 1 Martian gravity and 2 moon gravity parabolas. Okay, we are now in Mars gravity. In Mars gravity, I can do one-arm pull-ups, maybe.
Push-ups, push-ups like this. Yeah, like this.
I am the Martian.
We brought along some experiments to do in zero G.
So this is in about 1G of gravity. This is what the flame looks like on this barbecue lighter. Now we're going to try it in hyper G, and then we'll try it in zero G, and it should be.
We will see.
We will see.
We take it for granted that flames have this distinctive shape, but that's only because of gravity. The products of combustion have more energy and so move around faster and take up more space than the cooler air around them. Therefore, there's a buoyant force on them which is greater than their weight, and so hot air rises. This helps pull in the oxygen from around the flame to continue the reaction.
We're going through hyper G. I keep blowing out the candle because the stress of hyper G is significant.
In hyper G, this effect is magnified, since the effective gravity is almost twice as much. This amplifies the difference between the weight of the hot air and the weight of the cooler air around it, and so the hot air rises faster, making a longer flame.
Oh my goodness. Look how that flame just wafts in zero G because there's much less buoyant force to carry away. And so the combustion is not as good. You can see a lot of smoke coming off of that candle. That is incredible. Hey!
So we still have the gas flow. So this is why the flame is not circular.
It still goes up here.
It is not a sphere, but it looks very strange.
In zero G, the hot air is still less dense than the cooler air, but now there is no weight and no buoyant force. So the flame doesn't rise as high. This flame still maintains some of its shape because of the flow of fuel from the lighter. Otherwise, the flame would form a sphere, like on the space station, where it's very difficult to maintain the combustion reaction because it's hard for oxygen to access the fuel with all of the combustion products getting in the way. So if you're ever unsure about what the gravitational acceleration is where you are, well, looking at a flame is a pretty good way of finding out. I also brought along a slinky to try the slow motion slinky drop, but in zero G. Of course, here I couldn't dangle the slinky under its own weight, so I swung it around my head instead. The effect should be similar, with each coil stretched to provide the tension that keeps the length of slinky beyond that accelerating in uniform circular motion. I wanted to see what happens to the end of the slinky when I let go.
Here we go. 3, 2, 1.
Did you catch that? The slinky remained fairly stretched out and kept rotating at about the same frequency as before. Initially, I thought this was a boring result, but then I realized the reason the slinky doesn't contract is because weight was never part of this equation. The slinky stretched out in the first place because it was rotating, and since it's rotating after I let go, roughly the same amount of tension is required to maintain that circular motion, and so it doesn't contract. In zero G, it's possible to have a stretched slinky rotating in place without contracting. As long as the tension in the slinky provides the centripetal force, it'll keep spinning. This just goes against my intuition, which is made, of course, only out of experiences with gravity. Being weightless was an unforgettable experience, but maybe my favorite part was how it challenged my intuition. And that's the reason we need to do research in zero G.
I want to say a huge thanks to the team at Novaspace.
So that guy's pretty cool. If you've never looked at that website, he's got some really cool stuff and everything like that. So feel free to check that guy out sometime. All right, we got one more video for you. This guy's a British guy. He's kind of crazy, a little bit of fun, shorter video.
Take one.
What's your favorite browser extension?
Online shopping is easy.
Rather alarmingly, this aeroplane is known to its friends as the Vomit Comet. And that's a clue to the way it flies. It doesn't just fly along in a straight line like a normal airliner. This is where astronauts come to learn what life is like without gravity. This is a proper astronaut training exercise. The way it works, it's quite complicated. The aeroplane flies a parabolic trajectory, which leaves you effectively weightless when you're inside it. But the easy way to think of it is that it goes over an extremely long humpback bridge. I'd also like to boast that at no point in my life have I ever been sick on an aeroplane, or in a car, or on a boat, or on a fairground ride, or any of those things. But that might be about to change. This little pocket has a bag in it, just in case.
Before the space race, no one was actually sure if human beings could survive in zero gravity. Some specialists thought our internal organs would just fall apart and we'd drop down dead, or float away dead anyway. So the Americans sent the whole menagerie of animals into orbit to see what it would do for them, and they all survived. That wasn't really the point. The point was, would a man be able to do something useful in zero gravity? For example, operate a spaceship. So what they did was they sent a trained chimpanzee called Ham into orbit on the 31st of January 1961. Ham had been trained to pull a series of levers in response to flashing lights.
The red lever for the red light and the white lever for the blue light.
If he did that right, he was rewarded with a banana-flavoured chip. If he got it wrong, he was electrocuted.
Ham is laced in his couch and wired for sound. The electrodes on his feet will give him a gentle shock in case he forgets.
It's a parlour. Sorry. Hello. And this is where this child's game comes in, because it's a very, very similar thing. What happens is these lights go on in sequence. I have to get the same sequence when I press these two little buttons. If I get it wrong, it gives me a shock. Ow! And the chimp didn't have any problem with this. And he was doing it in 0G, which I'm going to try in a minute. I've forgotten. I hate this thing. Here we go. It was that one, wasn't it? Yes, it was. Well, I can do it. Sorry. I can't do it.
So obviously he kind of loses his mind, I feel like a little bit. But I will be honest, I've always thought like what an unbelievable experience that would be. All right. So our crazy British guy, the fun guys up there. But there you go. You'll have some practice problems. And I know this was a long video, but there were some videos on there, but practice problems. And then we'll be doing another lab, and we'll be using those IA lab skills that we've been trying to work on to help us get ready for our real IA. All right, everybody. Have a good one, and we'll